Hi everyone, we'll be talking about magnetic properties today, which is chapter 20 in your book, William D.Callister, and this will conclude our lecture series. Well, we've seen so far mechanical, electrical, thermal and optical properties, and we're left with the magnetic properties, which we will cover today. Of course, with the scope of talking about the matter, magnetic property relationships, of course. As any other lectures series for the properties, I'm going to start talking about applications first. Well, we came a long way from invention of the compass to the utilizing the magnetic property materials in refrigerator magnets. Of course, it's a fun way of utilizing it, but nowadays there are some more important application areas that we can discuss. For example, the maglev, they call, I believe, magnetically levitated train, as high-speed train, pretty popular in Japan, I believe, utilizes this property. Or it is used in medical field. Well, everyone knows the MRIs, like the imaging techniques that are used in the medical field. Or in the recent years, people developed nano-magnetic particles that is used in drug delivery or even cancer treatments, right? The tumor treatments in the cancer, targeted treatment. Or very old-fashioned application, of course, the recording the magnetic storage, your hard disk in your computers, or excuse me, or the old-fashioned tape recorders, right? They work with the magnetic recording, magnetic storage principle, or the scrap metal lifters. In the recent years, this is called the giant magnetoresistance effect. You create interchanging magnetic and non-magnetic materials one after another, and by playing with the magnetic fields, you can either block the electron movement or you can let the electrons move, and you can just process the signal really fast, utilizing the magnetic property in magnetic field. Okay, so there are some more important application areas, of course, but just to give you a little taste before we start the new jargons. First, throughout this lecture, we'll make an introduction to the definition of the magnetic field, magnetic dipole moment, magnetization, those concepts. And after we talked about those concepts, we're going to talk about the materials behavior, magnetic behavior, as diamagnetism, paramagnetism, defining ferromagnetism, antiferromagnetism, FERRIMAGNETISM, superparamagnetism, superconductivity. So we have, it looks like we have quite a lot, but we'll see. I don't think it's going to be a long lecture. So first, let's define. I'm going to be correlating this magnetic dipole moment or magnetic field with the electric field, okay? So first of all, if you have a dipole moment, magnetic dipole moment, it is always from south to north, right? S to N. And the magnetic field, on the other hand, is the opposite direction. So if we correlate the magnetic dipole moment to the electric moment, we can correlate the magnetic field to the electric field. So this may be like a negative and to positive end in the case of electricity, and electric field is going from positive to negative, right, the opposite direction. So just like that, magnetic field is the opposing direction to the magnetic dipole moment. So how can you create the field, magnetic field? It's basically, the magnetic field is created by movements of charges, right? So if an electron, for example, is moving in a coil like this, with a length of L, and if there are n number of turns in this coil, I can create a current with the right hand rule. I can I can create a magnetic field. With the right-hand rule, I can find the direction of the magnetic field as well, right? If my fingers are pointing the current loop, right? My thumb will be showing the direction of the magnetic field, of course, generated by the negative current, right? So negative electrons movements that created the current, right? And the strength of that magnetic field can be determined by this equation here. Of course, longer the length of it, smaller the current, or more numbers of turns at a smaller length. If you create those turns, larger number of turns at a smaller length, what do you create? You create a larger magnetic field. So this magnetic field created by this current, the movement of the charge, has a certain magnetic flux density. And magnetic flux density and the magnetic field are correlated with a certain permittivity. This is for the vacuum. If I multiply the created field with the permittivity of the vacuum, I get how much magnetic flux density I created there. If I put a material in between, right in the center of it, instead of a vacuum, then it's no longer the vacuum, there's a certain material, and that material has a certain permittivity. And that permittivity is just like the dielectric constant that we've seen in electrical properties, is related with the vacuum's magnetic permittivity times a certain relative permittivity number. So let me put myself up there. So the magnetic induction that is resulted in the material can be calculated by the field strength times that material's magnetic permittivity. We can also calculate this magnetic flux density created in the material with this equation here. That relates this time not only the field that you created, but also the magnetization, the capability of the magnetization in the material. Okay, as a function of magnetization, I can calculate the magnetic flux density in the material. Okay, so the jargons that we introduced so far is summarized in this table, like magnetic flux density, the magnetic induction in the material, which is B, magnetic field strength is H, magnetization is big M, and permeability of a vacuum and relative permeability, and their units are given in this table. We haven't talked about the susceptibility yet, but we will in a second. Okay, we just said the magnetic flux density can be expressed as a function of the applied field and the magnetization. Magnetization, on the other hand, is also a function of applied magnetic field with a factor that is multiplied with, which we're going to call the magnetic susceptibility of the material. And this magnetic susceptibility can be expressed in terms of relative permeability, magnetic permeability of the material. So if we combine all these together, we can put it in a common multiplication factor of applied field, the vacuum's permeability, times 1 plus the magnetic susceptibility of the material gives how much magnetic induction or magnetic flux density that is introduced in the material. So if we draw B versus H, we can generalize different kind of magnetic behavior of materials as such. If the vacuum relative permeability is given here, B as relative permeability of a vacuum is what? 1, right? Because nu is equal to u0. So if the nu is equal to nu0, nu r is being equal to 1, then my magnetic susceptibility of the vacuum is 0. Okay. So around this vacuum, having no material at all, indeed, we can compare our materials' magnetic behavior with respect to the vacuum. So, if a material's magnetic susceptibility is less than 0, a negative number, we call it a diamagnetic material. If it's slightly above 0, above this vacuum level here, we call that a paramagnetic. And if it's way over that, then we're going to call that a ferromagnetic, which is a permanent magnet. We'll define in a minute in the upcoming slides. In the case of this ferromagnetic materials, you can pay attention here. This applied magnetic field, the strength of the applied magnetic field is so much smaller than the magnetization, then we can assume the magnetic flux density as just being equal to relative permeability times the magnetization in the material in the case of a permanent magnet such as ferro or ferrimagnetic materials. Okay. Here at this point I'd like to make an analogy again to the electric fields and electricity. Maybe it will make more sense to you when we're talking about these terms here like magnetic flux density or magnetic field. Of course, this magnetic field's relevance in the electricity is the electric field, right? The magnetic flux density we created can be made an analogy as dielectric displacement, for example. This mu here is of course, the dielectric constant that we're using, the epsilon, if you remember from the electrical properties, and that magnetization here can be resembled or correlated to the polarization in the material. Sorry, I was just dealing with something else. Okay, this magnetization here we talked about here can be also correlated to polarization that we talked about in the electrical properties. Maybe that might help to have a little bit better understanding of the new jargons that we learned here so far. If the magnetic field is created by movement of a charge, then if you think about an atom itself has a constant movement of these charges in itself, right? What charges we're talking about? The electron. Of course, there are two types of magnetic moments that we'll talk about. One of them is orbits, because electron does two movements, right, around the atom. One is it's coming from orbiting around the atom, which we'll call the orbital magnetic moment. And also it does this spin around itself, right? So that's what we're going to call spin magnetic moment. Because of these two magnetic moments, we have an extremely weak magnetic field created internally in an atom. So these electron spins can be up or down. Of course, for each up or down spin, we're going to have this Bohr magneton number. For up, positive. For down, it will be a negative. Okay? For the spin magnetic moments. So these are some of the room temperature susceptibilities for dia and paramagnetic materials. Of course, as you can see here, the susceptibility that we talked about in previous slides are on the order of 10 to the minus 5 for diamagnets, and it's negative. And for the paramagnetics, it's on the order of 10 to the minus 3 to 6. It varies in between, which is fairly close to 0 value at vacuum, which is for paramagnets, it's above, and for diamagnets, it's below, as you remember. Okay, so how does this the materials ferro, ferri, para, or diamagnetic properties arise? How does that? First of all, it of course lies in the atomic configuration or the atomic electron configuration of the material, right? So if you look at iron, cobalt, and nickel, these are ferromagnetic, very famous, the most famous ferromagnetic materials, right? On top of it, I think gadolinium, right there somewhere, 64, right here, or neodymium in the recent years, and so on, are counted as ferromagnets, right? So the reason for that is when we call a diamagnet, it's the main behavior of the material is this. When we apply a magnetic field and when there is no field present, let's divide into two categories. When there is no field present, in diamagnets, we have no magnetization in the material, spin magnetization in the material, let's call, that up and down spin that we're talking about in the material at all. They cancel each other out, okay? There's no net spin moment. The magnetic moments arouse from the spin moments. So what diamagnet is, almost all material has this diamagnetic behavior, but it's only observable when there is no other magnetic behavior present in the material. For diamagnet, if no field is applied, overall there is no magnetization in the material. But as we apply the magnetic field to the material, because of the change in the orbital motion of the electrons in the opposite direction of the applied magnetic field, this change in the orbital motion of these electrons, we're going to observe an opposing magnetization in the material, which we call diamagnetism. We're going to revisit diamagnetics in the discussion of superconductivity. But what really is happening is it's repelling the applied magnetic field, basically. Okay. On the other hand, both para and ferromagnets under the applied magnetic fields, they have a parallel aligned spin magnetic moments. Okay. So, but when there is no magnetic field present, in the case of a paramagnet, since because of these magnetic moments are randomly oriented in the material for each atom, overall there is no residual or there is no permanent magnetization in the material. Neither diamagnetics nor paramagnetics have no permanent magnetization in the material. But the reason for diamagnetics having no permanent magnetization in the material is because all those magnetic moments cancel each other out, innate. But in the case of paramagnets, there is these magnetic moments present for each atom, but because they are randomly oriented under no magnetic field, overall magnetization is zero. But when the magnetic field applied, both paramagnets and ferromagnets align and act like a magnetic material. Okay. Among all these behaviors, ferromagnets are permanent magnets. Even if I remove after I align these spins, magnetic moments, all those magnetic moments are permanently reside in the material. That's why we call them permanent magnets, ferromagnets. So this is another way of showing that. In the case of a diamagnetism, as you can see, as we apply the magnetic field, the plate here, actually it repels the piece that has this diamagnetic behavior. On the other hand, for paramagnetism, if there is no field present, we have no overall magnetization. Under the magnetic field, both para and ferromagnets act like a magnet, of course. Okay, so there is an overall alignment in the magnetic moments. This is an example from your book. It's a nice example talking about the saturation magnetization. What a saturation magnetization is, based on the applied field, how much of these magnetic moments are aligned. Of course, how many of them being aligned has a certain saturation point. And where is that saturation point? It is related with the number of atoms, of course. So the question is asking, that's the maximum point that you can magnetize a material. That's called the saturation magnetization, okay? So calculate the saturation magnetization and the saturation flux density, which is what? B, right? For nickel, which has a density of 8.9 grams per centimeter cube. Why do we need the density? Because from density, we can calculate how many atoms do we have. The number of atoms, let me bring it to the front. So we can calculate how many atoms do we have. So that calculation, the number of atoms, will relate to amount of magnetization, the maximum amount of magnetization I can accomplish in the material. Why? Because I'm limited with the number of magnetic moments each belong to the atoms composing that volume. Okay. So to find the magnetization, what do I need? I need number of atoms, of course, for the given material. I need the more magneton number, which is 0.6 as given before, 0.6 times nu B. Well, the only unknown here is N. Once I find the N, what can I calculate? I can also calculate the magnetic flux density that I created in the material by multiplying with the vacuum's permeability. Well, that's what the question solution is doing here. Of course, we are given the density for nickel. Density times the Avogadro's number over the weight per mole for the nickel gives me what? After the cancellation of these units, how many atoms per meter cube do I have? So once I find this many numbers times the Bohr magneton number specific for the nickel, just plug and play, multiply it, we find the amount of magnetization that is created in the nickel, right? So from that number, we can move to, by multiplying this number with the vacuum's permeability, we can calculate the saturation flux density. Why it is called the saturation flux density? Because this is the maximum maximum amount of magnetization that we can create in the material if all atoms and magnetic moments are utilized. So we introduced diamagnetism, paramagnetism, ferromagnetism, right, in the previous slides. Now we're getting into a new jargon, antiferromagnetism. So what is antiferromagnetism? As the name speaks itself, the material has the potential, if all magnetic moments were aligned in the same direction, has the potential to be ferromagnetic. But because of the atomic configuration or atomic placements in the crystal structure is as such that their magnetic moments are interchanging from atom to atom, up and down, anti-parallel. Overall, we see the material, this is manganese oxide, we see overall no magnetism in the material at all. So that's why it is called antiferromagnetism. Let's introduce another jargon, FERRI-MAGNETISM. Both ferri and ferromagnetic behavior creates this permanent magnet behavior. Among all these behaviors we called, diamagnetics can be counted as anti-magnets, right? They're not magnetic at all. On the other hand, they're opposing to the magnetic field. It's repelling it. Paramagnets, because of this random orientation and overall, we see no magnetization at all in the material, unless there is an applied magnetic field. Under the magnetic field, it acts like a magnet. But ferromagnetics, on the other hand, are responding to the magnetic field by parallel alignment, and even in the lack of any field, they still stay as aligned, so they are permanent magnets, they're called. Just like ferromagnets, ferrimagnets are also permanent. But unlike ferromagnets, we have parallel and anti-parallel alignment of atoms because of the crystal structure and atomic configuration in the crystal structure. First of all, let's give an example from this inverse spinel structure, this cubic ferrites. Fe3O4 is the compound. In this compound and in this crystal structure, there are two types of iron valence states. One of them is +2 iron, the other one is +3 iron. And their stoichiometry is +2 being 1 over 2 times as much there are +3 valence state iron. And in octahedral sites, certain amount of these +3 valence state irons are present, but only in the tetrahedral sites, only iron +3 is present. So if you look at these yellow and green ones, these guys, like in the octahedral sites, +3 irons, you see it's upspin. Or in the octahedral sites, these +2 irons are upspins. And in the tetrahedral site, +3s, this time they're downspin. Since the ratio stoichiometrically is not equal to each other, these +2s and +3s, and their spins are in the octahedral sites, although they are parallel, in the tetrahedral sites they're anti-parallel, there is a partial cancellation of these spins. So overall, if you look at the material, we see certain amount of permanent magnetism. So that's why it's not as big as the ferromagnets, but it still has certain strength, which is also permanent, just like ferromagnetism. Okay, so this here summarizes the up and down spin cancellation and net magnetic moment creation in the ferrimagnets. Okay. So since both ferro and ferrimagnets are permanent magnets and they don't require a presence of a magnetic field to stay as magnetized, just unlike paramagnets, right? In the case of paramagnetism, what do we require? They act like a magnet, but only in the presence of a magnetic field. Ferro and ferrimagnetism has some common features and some differences. Let's take a look at them. There's a coupling interaction between magnetic moments of adjacent atoms and cations. Of course. So in both ferro and ferrimagnetism, this is present. They both form domains. We're going to see what domain is in the upcoming slide. A magnetic domain, just like crystal domain, right? There will be areas where there is all up, or it's magnetized, or in certain areas it's not magnetized. So we're going to call them domains, okay? And their spins will be magnetic orientations will be different. We'll see. But anyhow, both ferro and ferrimagnets form domains. Hysteresis curve, we'll see in the upcoming slides. They both display hysteresis curve. They're both, which in other words, they both are permanent magnets indeed. Magnetic moment coupling is parallel for ferromagnetism. We already seen that. They all are, the magnetic moments were all in the direction of the magnetic field, right? But in the case of ferrimagnets, there are partial cancellation of parallel and anti-parallel, and overall we get a certain direction of magnetization in the material, right? So there are, although in the ferromagnets all magnetic moments couplings are parallel, in the ferrimagnets it is anti-parallel. Okay. For ferromagnetics, being metallic, are relatively good conductors. Ferromagnetics are ceramics and insulating. Of course, what was that? It was an inverse spinel Fe3O4 structure, right? And what is a metal oxygen combination? It is a ceramic, right? Saturation magnetization are higher for ferromagnetic materials, of course. Why? Because it lies here because all is parallel, so there's no cancellation. So we have higher saturation magnetization for ferromagnets. There is also an effect of temperature I'd like to talk about. This red here is a ferromagnet, and Fe3O4 we already seen that is a ferri magnet, right? Ferri magnet and ferromagnet. This is the amount of saturation magnetization. As you can see here, this is almost 3 times more magnetized. The saturation is much larger. But as we increase the temperature, what is happening is that net parallel or anti-parallel magnetic moments will be able to, will start to jitter, right? So like as I increase the temperature, I'm gonna be giving a possibility of those moments to switch direction. So as I increase the temperature more, I'm increasing the probability of these magnetic moments to switch back to the anti-parallel states. So overall magnetization in the material, what happens as I increase the temperature? It decreases, of course. So as I increase the temperature to a point, the magnetization decrease. Saturation magnetization is way up there. And then as I decrease the temperature, look, it goes all the way down to 0. There is no magnetization in the material at all because all parallel aligned magnetic moments are now, with the effect of temperature, either became anti-parallel and they cancel each other out, right? So that temperature where this magnetization becomes 0 is called the Curie temperature. Above that temperature, there is no magnetization in the material at all. Curie temperature determines at what temperature I break this permanent magnetization property of that material. That's actually what that Curie temperature is. Yeah, this is the domain that I've been talking about. Please do not mix the domain with grains, okay? Of course, the material structure grains is important, but what magnetic domain is, you can see here, this is a neodymium, I think, alloy with iron and boron here. You see all these are the microscopy images. All these are, as you can remember from the previous lectures, are single crystal grains, right? All these are grains. So these are grain boundaries, if you remember. But within each grain, you see dark and light regions here, right? So these dark regions, let's say, are aligned up. The light regions are maybe magnetic moments down. So you can see maybe here better in this drawing here. What separates this one domain from the other domain is the overall alignment of that magnetic domain, okay? So here these dark and light regions are called different magnetic domains, although they are in the same grain, in the same crystal domain, okay? Don't mix the crystal domain with the magnetic domain. They are two different things. So when we look at the response of those domains to the applied magnetic field, it first will take time to adjust because look here in this picture, I didn't draw your attention to here. In between these domains, there's a domain wall where this net magnetic moments are switching, right, the direction. So where they're switching the direction, those regions are called the domain wall, okay? So first, it needs some adjustment as I increase the magnetic field, so the magnetic induction in the material flux density is not increasing much. But after a certain magnetic field applied, then it is quickly raises the amount of magnetic flux density in the material as I increase the field. And as I approach to a certain value, what is that? We've been talking about it. This is called the saturation magnetic flux, right? Density, or saturation magnetization value, where it's corresponding to. That's the maximum amount that I can harness from that material, right? With the applied magnetic field, where all possible net magnetic moments are aligned, is called the saturation point here. So therefore it starts with adjusting itself, then it increases with the increasing field. Then what happens as it approaches to the saturation magnetization, it decreases the rate at which we are utilizing the net magnetic moments with the applied magnetic field. Both ferro and ferrimagnetic materials shows this initial magnetization curve, but this is called the hysteresis curve. This hysteresis curve, as you can see, initial magnetization do not match with the rest of the story. What is the rest of the story? Let's say I apply the magnetic field and then I magnetize and saturated the material to this point S here. At this point S, even if you raise the magnetic field, what's going to happen? Nothing, because everything saturated, all possible net magnetic moments aligned with respect to the magnetic field. If I want to reverse this process, in other words, if I apply a magnetic field that is in the opposing direction, this time I'm changing the field's direction to the opposite direction, what is happening is it is not following this line. For ferro and ferrimagnets, we call this as hysteresis curve. This is this means as I reverse the direction of the magnetic field, the material will have a certain amount of magnetization left over in the material, even if I applied the exact same amount of magnetization in the opposite direction. Look, I applied this much magnetization in one direction, and I applied in the reverse the same amount of magnetization in the reverse, and just changed the direction of it. It didn't go back to its original zero magnetization point. It came back to a point where there is a certain amount of alignment still residual in the material. Net magnetic moment reside in the material. That's what it is. So that point is called the remanence. Remanence of a magnet is how strong it retains the magnetization in the material. But if I want to completely reverse this process, in other words, if I want to remove any kind of net magnetic moment alignment in the material, if I want to remove all of it and go back to the original zero magnetization point, it's the amount of energy or the amount of magnetic fields I have to apply to the material is called the coercivity of the material. So if I want to go back to the zero magnetic flux density in the material, then instead of applying the same amount in the opposite direction, I have to apply this much more magnetic field in the opposite direction. That's what a coercivity of the material is. So this hysteresis curve is exactly mirroring on the reverse magnetization. Of course, as I apply more magnetic field in the negative direction, what's going to happen? It's going to saturate again on that direction, and it will follow that remanence and coercivity in the positive direction again. So this S-shaped initial magnetization is not followed when I reverse the magnetic field. How fat this hysteresis curve will determine how much magnetization this material can create, okay, in itself. Of course, this is the maximum saturation points in between for the positive and negative magnetic field application, but also we don't have to apply that maximum magnetic field to the material. We can also apply certain amount. This green curve here is showing that is a little hysteresis curve here showing for the amount of magnetization that I applied that is not in the saturation limit. Okay, so I can draw many hysteresis curves within that maximum saturation case based on applied magnetic field, of course. So if you compare ferro and ferrimagnets, we're going to have, of course, less of a saturation and in a ferrimagnets or ferromagnetic materials, but also very important difference for dia and paramagnetic materials. We're going to have this linear change in the magnetization in the material. Why? Because as soon as we apply the field, what happens? Instead of having this alignment of the boundaries and then increasing and saturating it, for the diamagnetic and paramagnetic materials, as soon as we apply them, either in the opposite direction for a diamagnet or for paramagnets in the direction of the field, we're going to have an alignment, overall alignment in the crystal structure. So that's why we're going to have a linear behavior for initial magnetization. And we're not going to have any hysteresis curve neither for dia or paramagnetic materials because of this linearity. But on the other hand, for ferro and ferrimagnets, we have this S-shaped initial magnetization, which is followed by that hysteresis curve for reversing the magnetic field. Also, there is an important property we can talk about, which is magnetic anisotropy. Of course, think about iron. This is nickel, and this is cobalt. So remember from the periodic table, these are the infamous permanent ferromagnets, right? Of course, if this is the atoms, and each atom's electrons is contributing to this magnetization. Remember from the crystal structure, chapter 3, if I go in different direction in these crystal structures, take a look at it. Iron is BCC, nickel is FCC structure. So in the BCC structure, if I go in 100 direction, or 110 direction, or 111 direction, do I have same number of atoms? No. For BCC, for example, if I go along the 110 direction, I'm passing through how many centers? In the corner, one center. In the face center, sorry, for BCC, for 111, in the corner I have a one center atom. In the body center, I have another center atom, and in the other opposing body diagonal edge end, I have another center, right? So along 111, I'm passing through 1, 2, 3, 4 R. Along 110, I'm only passing through two centers of atoms, and along 100, again two center atoms, but these atoms are not equally separated, right? Compared to 100 and 110. The same story goes for FCC or even for HCP. Of course, because of this crystallographic reason, we're going to have different magnetization if I apply magnetic field in different crystallographic directions in materials. Okay, and this phenomena is called magnetic anisotropy. Jargon will introduce in the BH curve the magnetic flux density versus applied magnetic field hysteresis curve. We can define a magnet as a hard magnet or a soft magnet. A soft magnet is defined as with a little amount of applied magnetic fields. Here, as you can see, with a little amount of applied magnetic fields, we can easily get to the saturation flux densities. In the case that we call that a soft magnets. Another important property of a soft magnet is, yes, it is easily magnetized and saturated, but it has a very low coercivity. Okay. On the other hand, for hard magnets, we have a very large area that determines how strong of a magnet is our magnet. So we can also classify magnets as hard or soft magnets based on the hysteresis curve. Here are some examples of soft and hard magnetic materials. This phenomena, superparamagnetism, is not in your book. These two slides I put up because this is an important phenomena that is related with the material size, and it will be nice to know. What was paramagnetism? Paramagnetism is the material overall has magnetic moments, yes, but they're so random under no field, electric applied field. What happens to the material? It is not magnetized because overall it's zero, random oriented. But once I apply a field, what happens? This red curve here, it is linearly, it doesn't have a hysteresis loop, but it aligns with the magnetic field. Interestingly, certain materials, for example, this blue one is, let's call it a ferromagnetic material, and this ferromagnetic material is a hard magnet, right, because it's very large. But as I play with the material's grain size, making it either a single crystal or smaller crystal, depending on the particle size, as you can see here, either single domain or multi-domain, of course, we can play with the materials, how hard, how strong of a magnet it is, or how soft of a magnet I can make. Same material, just playing with the structure of it, playing with the how big my crystal domains are. Look, not magnetic domains, crystal domains, right? How big are the grain sizes? But very interesting phenomena occurs after a certain grain size that I go down to. If I go down to a grain size that is on the order of 10 nanometers and below, then the material, instead of being ferromagnets, material starts to act like a paramagnet. But this paramagnetic behavior, if you compare with another paramagnet here, that will be a very, very small slope, linear slope next to it. I don't know if I have it somewhere here. Yes, here. This green one is a regular paramagnetic behavior. But here, this red one is super paramagnetic behavior. The reason why they put a super in front of paramagnetic behavior is because it is fairly strong, okay? So with the amount of magnetization, same amount of magnetization compared to a regular paramagnet, we're getting much higher saturation flux densities. But what happens is, after a certain size, as you go smaller, this time each crystal domain acts like an atom, okay? So instead of taking these, ferromagnet becomes a super paramagnet after below a certain size. The reason for that is these domains are like acting like an individual atom paramagnetic behavior. And I don't have the thermal energy is sufficient to change the direction of the magnetization of the entire crystallite. So with a little bit fluctuation in the thermal energy in the system, we can play with the, instead of field, the magnetic field I'm talking about, I can play with the direction of the magnetization of the whole entire crystallite. And the material behaves in a manner very similar to paramagnetism, except instead of each individual atom, in the case of a paramagnet, being independently influenced by an external magnetic field, this time the magnetic moment of the entire crystallite aligns with the magnetic field. Okay, so this phenomena is called the superparamagnetism. So let's now talk about superconductivity. A superconductivity, at below a certain temperature, certain materials act like there is no resistivity in the material at all. So let's talk about the resistivity. Let's remember that from the electrical properties section. If you take a regular metal, for example copper, as I increase the temperature, what happens? Because these electrons will be scattering a lot more, then the overall electrical conductivity drops. In other words, the resistivity increases as I increase the temperature. So if I decrease the temperature, the inverse effect is dominant. What? As I lower the temperature, the electrical conductivity increase, the resistivity will decrease because there will be less of a chance of scattering events, right? But in the case of a superconductor, yes, it acts like, for example, in a mercury, up until a certain temperature, the resistivity drops, but at a certain temperature, that critical temperature, below, which is a 4.2 Kelvin for mercury, absolute zero is 0 Kelvin, you know? So this is like 4 degrees Kelvin after the absolute zero. The mercury acts like there is no resistivity in the material at all. It drops to 0 all of a sudden after a certain temperature. So if I was to make a loop out of this mercury, since there is no resistivity, the current will flow infinite amount of time. So because there is no loss of energy, right? So the loop continues until infinity. So the superconductivity is no resistivity at all after a certain temperature. Below a certain temperature, the behavior of the material turns into a no resistivity at all below a certain temperature. So almost 20% of overall, if you take the whole world's electricity consumption, almost 20% of it goes to these resistivity issues. Like, think about if we were able to, as a material scientist, find a material that is superconductor at much higher temperatures, then we would solve the issue of that 20% loss in energy, in electricity, due to these scattering events of electrons, which goes to what? Which goes to heat. So you lose that 20% of that electricity into heat, okay, because of those scattering events of electrons. But in the case of superconductors, below a certain temperature, you don't have any resistivity at all. How wonderful it is, right? But the problem with that is, such low temperatures, to accomplish such low temperatures, we need to use coolers, right? So you have to cool it. How do we cool it down to those temperatures? If it is below 77 Kelvin, if it's above this transition temperature, this critical temperature of the material was above 77 Kelvin, we would be able to cool it with liquid nitrogen. But if you want to go to lower temperatures, then we have to use either hydrogen or liquid hydrogen or liquid helium. So both of these, helium and hydrogen, liquid hydrogen, liquid helium, they're both super expensive compared to nitrogen. So if you are trying to save from electricity, or some losses due to heat and resistivity losses in the electricity, then you have to cool it with a very expensive media such as liquid hydrogen or helium. So, but later this was the main problem. Like, superconductivity is wonderful, but to get that property in the material, you need to go down to very low temperatures. So it is still a very large area to still carry out research on, the superconductivity area. And I think as high as minus 70 degrees C transition temperature was accomplished to get the superconductivity, but under extreme pressures, hydrogen sulfide, I believe, ex-superconductor. But you have to apply extreme high pressures and cool it down to minus 70 degrees C. Okay, so these kind of research are still carried out, but later in 1987, above 30 Kelvin, different forms of barium, copper, yttrium in oxides form ceramics exhibit such superconducting behavior. So, for example, for this compound, this critical temperature was 90 Kelvin, and for this compound it was 122 Kelvin. So still you have to cool it down, but relatively cheaper media you can use, such as liquid nitrogen, to obtain superconductivity for these materials. So there's still some research going on, and still a large opportunity out there to find higher transition temperature superconductors. But what happens with superconductivity is, below that critical temperature, as soon as the material gets the superconducting state, it acts like a, if I apply a magnetic field to the material, it acts like a diamagnetic material. Let's remember what was a diamagnetic material. It is the field repeller, right? Because as I apply the material a magnetic field, the net magnetic moments in the material aroused from the orbital magnetic moments align against the applied magnetic field. So in turn, it repels the field. So that magnetic field, the value of magnetic field as it's increased, after a certain value, just like a temperature effect, after a certain value, this effect, the repelling diamagnetic property effect, disappears. So the diamagnetic behavior disappears. In other words, the superconducting behavior disappears. So just like temperature, the applied magnetic field keeping the temperature constant, if I apply a magnetic field to a superconductor and raise the value of that magnetic field, after a certain magnetic field value, superconducting behavior turns into a regular non-conducting or resistively conducting behavior. Okay, so this effect, this diamagnetic behavior of superconductors, that field repelling, is called the MEISSNER effect. Okay, so just like temperature, keeping the temperature constant, if I apply a magnetic field to a superconductor, after a certain amount, a value of magnetic field, superconducting behavior turns into a regular, normal, resistive or resistively conducting, higher resistivity electrical property, from superconducting to normal behavior. So this transition can be divided into two different types. There can be the response of the superconducting material to the magnetic field can be divided into two. Type 1 and type 2 type of classification, we call them. In the case of a type 1 type of classification, this transition from superconducting to regular normal behaviors happens at a specific magnetic field. Look, we have this here, the magnetic field applied here. As I increase the applied magnetic field, the material is still diamagnetic. In other words, it's still superconducting. But after a certain magnetic field, it cuts like a knife, like it's just at a very sharp transition from diamagnetic to regular behavior, superconducting to regular behavior. This type of materials are called type 1 type of materials. There is another way of this transitioning is occurring in between superconducting to regular behavior. And this time it's not as sharp. There is a transition region from a certain applied magnetic field to another magnetic field, which is designated as HC1 and HC2 here. This superconducting diamagnetic behavior to regular behavior is occurring slowly. There's a transition region or a range of applied magnetic field values for this kind of systems. We call them type 2 materials that causes a transitioning from diamagnetic superconducting to regular behavior. So the reason for that is the superconducting for the type 1 type of behavior is only occurring on the outer skin of the material. So this transition occurs really rapidly. But in the case of a type 2 type of materials, the current, superconducting current is flowing throughout the wire. So over all cross section. That's why it slowly loses its superconducting behavior as we increase the applied magnetic field. So, to determine the superconductivity limits, there are three main parameters. One of them, as we mentioned previously, we gotta be below a certain temperature. There's a critical temperature. Below that temperature, we get the superconducting behavior. Also, there is an effect of applied magnetic field. Below a certain magnetic field or below a certain range of magnetic fields, right, depending on type 1 or type 2, we're going to be having a superconducting behavior, diamagnetic, and above that value, we're going to have a regular behavior. There's a third important parameter that determines the superconducting behavior, is the amount of current density. As I increase the amount of current density in that material, the current, right, which is the current per for a given cross section, right, that is the current density, we're gonna start to have that scattering effect again. So the material will lose that superconducting behavior. Therefore, we can determine in what volume, based on these three main variables and main parameters: current density, temperature, and also the magnetic field, applied magnetic field, we are in a volume of superconducting state. If we are outside of this three-dimensional volume that is determined by these three variables, the material acts like a regular, normal. But if we are in that volume here, then the material exhibits a superconducting behavior. So according to the Tines law, we can relate the applied magnetic field, the critical magnetic field that we apply, and also the temperature. We can relate these two variables to each other. Okay. All right. So that's concludes the limits of the superconductivity behavior, and these are some of the materials that are exhibiting the superconducting behavior and their critical temperatures and critical magnetic field to change that behavior from superconducting to regular behavior. All right, that concludes our chapter. This was as I told you, a fairly short chapter, just like the thermal properties. So we put a check mark next to each of these jargons here. I hope you enjoy this class. I think this concludes our lecture series. I hope to see you in the future for other lecture series. Thanks for listening.